And that's good. Let me load the bullet. Let me actually inhale a little bit. That'll bring the bullet back into place. Sadly, once I do that, I can't look through there anymore, but I'll just look around. It looks like I didn't bump it too much. One more thing I need to do is to what we call activate the switch. Okay, so that activates the switch. And so now, if this works right, once it exits out of here, that can will begin to fall, the bullet will begin to fall, they'll fall at the same rate, and when they cross paths, they'll be at the same height, and of course then they'll hit each other. So let's see if I can hit it. And I've noticed that I only hit it when I put on the hunter's hat. So I'll put on the hunter's hat here and wish me luck here. All right, so I will load it up. And 1, 2, 3. Yeah! And I hit it. And so that's the three experiments here. Now, I have even more to show you. It's the same basic idea. Let me turn on the computer screen. It's more of an animation, but what's nice about it, now I can take this thing down, is the animation, and this is why I have to do an animation, allows me to turn off the effect of gravity. And I can't really show you that any other way without the animation. So let me turn on the projector here. And let me take a look at this little diagram here, which says projectile motion. And so I'll come over here and projectile motion. And unfortunately, it gets started right away. So let me go back to the beginning here. But right up here, you'll see there is one object. It kind of looks like a little black racquetball. Now this racquetball, if you will, I want you to really think that there are three of them. The real racquetball looks like this. And so here's my racquetball. And my real racquetball is going to just go, I'm going to give it a horizontal push. So horizontal, like that. But then, in this animation, you will see two other racquetballs. You will see a racquetball that instead of having a horizontal push is just dropped with gravity. And it just goes straight down. So in other words, it has only vertical motion, not horizontal motion. The other racquetball you will see is one where we're going to imagine giving it a little push and then there's no gravity. That's why I have to do the animation. And so you can imagine if I gave something a little push and then let it go and there was no gravity, it wouldn't fall down. It would just keep going in a straight line, right, at the same speed. That's Newton's first law of motion. Watch, I'll show you the animation again. So I'll hit play. Okay. And so this is what I'll call the real racquetball. But this is one that is a racquetball that is dropped straight down. And this is a racquetball that's going across the top with no gravity. Hopefully what you will see, and let's say each little flash here is 1 second. So why don't I go 1, 2, 3 seconds? It's right here. Notice that the racquetball with gravity has dropped down the same as this racquetball with no horizontal motion. And then also notice that across the top, the racquetball that had no gravity just keeps going at the same speed, is the same as the horizontal. And that's why I keep saying over here. And now we can actually do some numbers. We could say that nature has been really good to us. Nature did this for us. Nature said that the horizontal and the vertical are acting separately. And so when I start to ask this question, and it's really kind of the same question we did in chapter 2 and 3, where is the ball 1 second later, 2 seconds later, 3 seconds later. What we're going to do is do a calculation and just figure out how much would one fall and how much would one move over. Okay, let's watch it one more time, and finally we can do our calculations. Okay, so I'll come back here. Here's the motion. And so if I give us some numbers to work with, let's do this. And I can also remove this one out of the way. Actually, this pole might still get in the way. Let me just take this off, set it down. And it's getting close to a break time anyways. But let me do one quick calculation here, and then we'll come back and do the second lecture for today. But if you imagine that racquetball right here, and you give it a nudge of, say, 10 meters per second in a horizontal direction, and you ask this question like we did in the last chapter about time and distance and velocity, and I'll just put 0 second, 1 second, 2 seconds, 3 seconds. Let's just go for 3 seconds. And you ask, what is the acceleration? What is the velocity? And what is the distance? Let's ask that twice. You see, in the past chapters, I just made a little chart that said what is the acceleration, the velocity, and the position. But this time, what I mean is what are they horizontally? And I'll make a second chart which says what is the acceleration, what is the velocity, and what is the distance vertically. And this is what I was saying about 20 minutes ago when I got started here. The good news about these calculations, I hope you will see, they're easier than you might have first guessed. Because nature was really good to us. Nature keeps the components, the x and the y, separate. So we can do our calculations separate. And so a two-dimensional motion really becomes a one-dimensional motion twice. All right, so since we did vertical motion already in the past chapters, why don't I do that one first? Let me put my units up here. Let's measure things in meters per second squared, meters per second, and meters, same thing here. Meters per second squared, meters per second, and meters there. And then let's fill in this little chart. And even though the ball is going in 2 dimensions, as shown in this diagram, in your mind, I want you just to think about this one that is dropped. And since we've already done that one, I'll do this one kind of quickly. And so when I come over here, and even though I'm giving it a horizontal nudge, imagine if I just dropped it, what would its acceleration be? And I'll just put 10, which is a rounding of 9.8. And that's what we did back in chapter 2. We just said that an object that is under free fall would have a vertical acceleration. Now, we didn't use the word vertical, but we were saying its acceleration would be 10. It would be 10 in the vertical direction. So, here's where it gets a little bit harder. Now remember, I'm giving it an initial nudge horizontally. That's another way of saying I'm not doing anything vertically. So what is its initial speed vertically? 0. Don't mix that with, remember, I gave it a horizontal nudge. This is its original or its initial speed of 10. But I'm not putting 10 for vertical. Now that 10 is going to come over here under the horizontal one, okay? But this is the same as just letting a ball go with 0 speed. So we know if it changes by 10, it would increase by 10 every second. So starting at 0, it would then go to 10, and then to 20, and then to 30. And of course, the other one we did, and I should probably put the equation on the board because this one was kind of a little more challenging here. We need to look at its average speed. Although now that we just spent a long time deriving that equation, we could actually use this for the vertical motion because it does start with speed of 0 in the vertical direction, as we argued at the start of this lecture that, hey, there's actually a time this can be used, and then this would be appropriate this time. But again, I'm just going to stay away from that one. I just like this one so much better because it always works, whether the initial speed is 0 or not. And so if you look at this first 1 second, or at 0 time, you'd say, okay, well, going down vertically, is nothing yet. But note that this one comes out to be 5. Remember that 5 calculation? Remember we have to do the average speed? Remember during this 1 second, it would start at 0 and go to 10. So if we added those two and divided by 2, we'd get 5. So it's 5 for 1 second. And if you remember this one, we got a 20. You can go back and look at that video. But I'll say it again, it would be this. You would look at the average speed for those 2 seconds. And so you start at 0, you end at 20. That would be an average speed of 10. And 10 for 2 seconds would be 20. And then this one came out to be 45. And again, you can see it here, the average speed. So during these 3 seconds, it would have started at 0 and finished at 30. So its average of these two would be 15, and 15 times 3 is 45. And so I hope I didn't go too fast on that one, but I am going to say that's exactly the same numbers, exactly the same logic that we did back in chapter 2. And so go back to that video if you have any troubles with that, because what I'm trying to show you here is I'm not doing anything new. I'm doing exactly the same thing, but I'm doing it twice. I'm going to do it once for the horizontal motion and once for the vertical motion. All right, so that's why this chart I wanted to start first, because I already done this one. Let me now do something new, if you will. But this is a real easy one, because what's the acceleration horizontally? Now I'll come back over to this animation. This animation was trying to show you that the ball across the top would be something that would be like in outer space, something that had no gravity. And with no gravity, there is no acceleration. This is Newton's first law. It just keeps going at the same horizontal speed. And so what's nice about this is, here's what we're trying to say. What is the acceleration horizontally? 0. All right, so now we need to remember that when you say a projectile has an acceleration, there's 2 of them. There's one horizontally and there's one vertically. Okay, so the one horizontally is 0. The one vertically is the 9.8. So we've been doing the 9.8 for a lot. The other one that I need to introduce you to is the 0. And 0 acceleration is great, because 0 acceleration means don't change your speed. So let me come back to the very beginning. At time equals to 0, what is your horizontal speed? Well, that's what was given in the problem. It's 10. And if you don't have any acceleration, what would be your speed after 1 second? Yeah, still 10. And what would your speed be after 2 seconds? Still 10. And what would your speed be after 3 seconds? Yes, still 10. So this one, again, is the same logic, the horizontal, but it's actually even easier than the vertical ones, because the acceleration is 0. And so whatever the initial horizontal speed is, it keeps that all the way through. And so I think that's a little surprising, because if I were to really throw a ball hard, we kind of see it angle down, and I think the angling down gets interpreted as it's losing its horizontal speed, and that's not the case. See, that's what this is trying to say here. It keeps the same horizontal speed. It just gets more vertical speed. And so at some point, it's going down more than it's going over. And so that gives the perception that it somehow lost its horizontal speed. But it doesn't. It keeps the same value, although it's small. And so for the first second here, the horizontal speed is more than the vertical speed. But then after that, the vertical speed is more than the horizontal speed. And like I said, that can get interpreted in somebody's mind when they see this as thinking, oh, it slowed down horizontally. And it does not. And so that's what I'm trying to say here. And of course, that's what you see in this animation, and that's what you would expect in outer space, that it would go the same distance each time. It has the same speed, and so it just keeps going the same amount horizontally. And so I'll say it again. Chapter 4 here with projectile motion is hopefully easier than you might have thought at the beginning. It really is just doing one-dimensional motion twice. All right, well, let me continue on with this, because the harder one is usually here, although this isn't nearly as hard as this one. This one, we had to figure out what the average speed is every time. But if the speed is always 10, what is the average speed? It's always 10. You have a bunch of 10s, no matter, you start at 10, you end at 10. So your beginning is 10, your ending is 10. If you average those two numbers, 10 and 10, 20, divide by 2 is 10. So 10 times 0 seconds is 0 distance, then it's 10, then it's 20, then it's 30. And so it makes it really easy to do this equation. Notice, do not use that equation. Right? It does not have an initial speed of 0. But I would just keep using that same equation. The only thing is I don't have a 0 plus that one. I have a 10 plus a 10 divided by 2. And then that would be it. So after 3 seconds, and so if we come over here and look at our animation, and we call this a second each, so there's 0, there's 1, there's 2, and so there's 3 seconds. What I'm saying here is vertically down after 3 seconds, okay? So after 3 seconds has gone down 45, and over 1, 2, 3, 30. Now, sadly, I just realized looking at my scaling of my diagram, that's not drawn to the same scale. My numbers say it should go down more than over, and that picture shows it a little different. So that picture must be kind of representing a larger horizontal speed here. But that aside, hopefully you see how I did the calculations. So I'll say it again. Here's the neat thing about projectile motion. We're not doing anything new. We're just going to do the same one-dimensional stuff that we've learned in chapters 2 and 3 twice. Once for horizontal, once for vertical. And I'll do some more calculations, but now's a good time to take a break. And if this was, face-to-face, I'd say, hey, go take a break, relax your, mind for a little bit, relax your eyes, go to the bathroom, and get something to eat and drink, and come back, and we'll get started. So in this case, we'll just take a 20-minute break. I'll switch up the equipment, and we'll come back to these calculations, because it's good to see some more of those. But we're really almost done with the chapter.